Here you can see the characteristics of the diode, and if I plot this characteristics in a different way, because I have taken the scale is like this. Here my scale is like this. This is some zero point 0.1 volt, this is some 0.2 volt, this is some 0.3 volt, zero point 0.4 volt, zero point 0.5 volt. And if I redraw this characteristics with a larger scale, if I redraw this characteristics with a larger scale, then what will happen? Let us suppose this is 1 volt, 2 volt, 3 volt, 4 volt, like this. This is the V bias or the voltage across the diode, and this is the current flowing through the diode ID. So now you can see at some 0.7 value, the current will rise. So the characteristics will be like this. Okay. Now we will start the modeling. Okay. So before going to the modeling, there are two conclusions which are very necessary regarding the diode, and let me write those conclusions. So these conclusions are from the previous lecture. So these are the conclusions related to the PN junction diode. This VD we are applying like this, then this ID, the diode current is greater than 0. And VD, if we are applying like this, which is the reverse bias, then this diode current is approximately equal to 0. So you need to understand these two conclusions, that this diode current is approximately equal to 0, and uh, this diode will be conducting, and this diode will be blocking. So now you need to understand these two conclusions, blocking and conducting. So this diode is not conducting and or blocking, and this diode is conducting. So when we are applying the external bias in some special manner, so and when we are connecting this P terminal to the positive and this N terminal to the negative, then the diode conducts and a current flows. And what kind of current is this? That this we have already discussed in the previous lecture. This is diffusion current and all those things. Now we will not talk about all those things again and again, because we have already studied all those things in the semiconductor physics. This ID is greater than 0. Okay, and VD we are applying here. VD is, again we can say that VD is also greater than 0, and this ID is 0 when applied VD is less than 0. Okay, so this is the conclusion from the previous lecture, and this you need to remember, and this is very important, and with the help of these two conclusions you can solve the many numericals. And now we will come to the modeling. So there are three kinds of modeling that can be done related to the PN junction diode. So basically in the modeling, what we are doing, we represent the exact characteristics with the help of some other elements. We need to represent the characteristics. Okay, so this is the characteristics of the diode. If somehow by some other elements, known elements, I can represent this characteristics exactly. If the characteristics of this device, actually let me draw the symbol of diode. First time I'm drawing the symbol of diode. This is the electrical symbol of diode, and the voltage across the diode is called VD, and the current which is flowing inside the diode is called ID. And this arrow indicates that this diode allows the flow in one side, and this bar indicates it blocks in the other side. And in the next lecture, I will give you the analogy, the mechanical analogy for the semiconductor diode. Okay. So here, let us understand the modeling first. So in the modeling, we try to replace the uh, device. We will try to replace this device from the circuit by some equivalent circuit. So that are representing almost the same characteristics by some known other elements, by some known elements or some other you can say those elements or some other situations which are representing the same kind of equation. So this is the modeling, and here we will try to model. And why we are modeling, this should be clear, because we cannot use the non-linear equation which we understood, and the Shockley equation. We cannot use the Shockley equation in the analysis of diode in the normal circuits by the conventional network theory. So here we will learn the first model. The first model is the ideal diode model. First model is the ideal diode model. So in this model, we need to understand two things. We represent when the diode is conducting. So what we do in this model, we approximate this value because this is very near to this. So if I neglect this 0.7 volt, if I neglect this 0.7 volt, then my characteristics will be like this. If I neglect this 0.7 volt, then the characteristics will be like this. Here you can see the current is 0, and as the some voltage is appearing against the diode at some when the VD is less than 0, then ID is 0, and when VD is just changing from negative to some positive value, then the diode current is ID is greater than 0. So you can understand this thing. So we will use this mathematical expression in order to find the modeling for this ideal diode. So here you can understand ID equal to 0. So I am representing the model. So here actually what I have done, I have replaced this, I have approximated this value, this 0.7 I have neglected. And if I have neglected this 0.7, then I am representing this by this line only. Okay. So we can represent this line only because this 0.7 is the value here, and I am neglecting this. So we will represent this ideal diode model with like this. So this will be the characteristics. So it will coincide with the x-axis and y-axis. So here the characteristics will coincide with the x-axis, and here the characteristics will coincide with the y-axis. Okay. So if you see this characteristics here, at the ID, at the y-axis we have ID, and at the x-axis we have voltage V. And now I will represent the diode here. So here first we will try to represent the diode here. You can see here, if the current is 0. If I try to analyze this portion, before the voltage is positive, okay, when the voltage is applied, voltage is negative. When we are now, you can see in this kind of characteristics we have two parts. One part which is coinciding with the x-axis, and the other part which is coinciding with the y-axis. So now what you need to understand, this part and this part. For this part we will try to model. So if I want to model this part, then you can see here that the current here id is 0. Current here is 0. So if the current is 0, though, how can you model the current if the current is 0? What is the situation in the circuit when the current is 0? So this is the open circuit situation. So if the current is 0, then I can model my device. If the current in some device is 0, then we can say it is open circuited. Then definitely I can represent my diode in ideal characteristics. In ideal characteristics, I have approximated this value, which is very near to this, because if you are seeing by this diagram, then the difference is large, but you can see the scale is different here. But I have rescaled the diagram here, and in the rescaling you can see it is very near to the x-axis, y-axis. It is very near to the y-axis, and I have approximated this for the y-axis, and the characteristics now is this only, which is coinciding with the x-axis and y-axis. And now I am writing or I am doing the modeling for this id equal to 0. If id equal to 0, then definitely I can represent my diode as a open circuit. Okay, so diode, we can represent a diode as a open circuit, and for this portion, when id is greater than 0, and what else we can see here, the id is very large, and you can see the voltage. Yes, the voltage is almost 0. If the voltage is almost 0, then you can represent, because id is just greater than 0, and id greater than 0 cannot indicate any specific parameter, any specific circuit situation. Here, when id equal to 0, then it indicates open circuit, but id is greater than 0, then it might be any value. So we cannot represent this thing, but we can represent vd equal to 0. So if I want to represent here vd equal to 0, then we know that if the voltage across some circuit is almost 0, then it is like a short circuited. Because voltage is 0, and we can represent it by just a wire. It is a short circuited, and it can flow any amount of current. And the voltage across is 0, almost 0. So it is a short circuited thing. And one more way of understanding this thing, here you can see, if this is I and V, one more in let me tell you one more way, and we will conclude with this ideal diode model, and the other two models we will cover in the next class. So id is greater than 0, id equal to 0, and we need to model this thing. And again, one more way of understanding this thing. So this is the line here, you can see. So if I try to calculate the resistance here, what will be the slope of this line? Delta I by delta V. What is the slope? Change in perpendicular value on the change divided by the change in base value. And here you can see the slope is almost equal to 90 degrees. So this delta I by delta V is equal to 90 degree, which is 1090. 1090 is infinity. If this is infinity, then this voltage change is almost equal to 0. This, or you can say delta V over delta I. One more thing. What is the resistance of the in the any device? Delta V over delta I. So by the resistance concept, you can understand. So this, if delta I over delta V is infinity in this portion, if I name it AB, in the portion AB, this delta I over delta V is infinity for this line. The slope is 90 degree. You can understand by the normal coordinate geometry, the slope of this y axis, this is making 90 degree angle with the x axis. So you can understand the slope is 90 degree. And in terms of change in quantities of x on the y-axis and y-axis and x-axis, we can write it delta I over delta V. So this delta I over delta V is infinity. Then we can write R equal to delta V over delta I, which will be equal to 0. So the resistance of device will almost equal to 0, and then we can we can treat it as a simple wire, because for a wire the resistance is almost 0. And if we try to calculate the resistance for this, then again you can see the slope is 0 degree. The slope is 0. It means delta I over delta V is tan 0 is 0 for this portion, for this OA. For this is for AB. For this OA, delta I over delta V is 0, and the resistance is delta V over delta I, which is equal to infinity. And if the resistance is very much high, almost infinity, then we can represent that thing as a open circuit. So there are two ways in which you can understand the ideal diode modeling. So here we have modeled the here we have modeled the this characteristics of this diode in the ideal manner. So we have taken this approximation, and after taking this approximation, just mathematics, by using our mathematics we have done the modeling. So in modeling there is only mathematics. Okay, so we are trying to represent the equivalent thing. So here you can see, now we can replace this thing as this. So one last thing. So how can we use this thing? So just one circuit I will show you. If my diode is here in this circuit, and there is one more circuit like this, where the polarity is changed. So how can we use this modeling here? Because as a device, we must know the characteristics, because for a resistor I know the current flowing in the resistor is given by voltage across the resistor divided by the resistance. And similarly, there must be some kind of modeling for the diode, and we have created the ideal diode modeling. So how this ideal diode modeling will be used? Here you can see, if this is like a 5 volt here, then definitely this 5 volt is a positive. We have connected the positive of the battery this with this, and the negative of this is connected to the P side. And now you can see this, we can use this modeling here. So now this, if this diode is a ideal diode, if I am using this diode as an ideal diode, and we are using the ideal diode modeling, then what will happen? We will replace this diode with the short circuit. Why? Because this is in the forward bias. Because this is in the forward bias, it means the characteristics will lie here. The current will flow. And the ID is greater than 0. So we are the diode is conducting. Diode is conducting here ID, because we have applied the positive. Because this voltage will try to elevate the potential of P side, and will try to decrease the potential of N side. Then definitely the diode will conduct. Then ID will be greater than 0. So here by using this modeling, we can calculate the current ID. This is the resistance. Then ID will be 5 by R. So now this is how we can use the modeling inside the circuit. One more example: when I have reversed the polarity, then we have connected the negative with the P side, so it will decrease the P side potential. Then definitely it will increase the level. So it will increase the level of the potential barrier, and the diode will be in reverse bias. And in the reverse bias, the situation is this. The ideal situation is this. Actually, this is the real situation, but I have modeled this situation as here. So ID is less than 0. ID is less than 0. Sorry, ID is equal to 0. ID is equal to 0. it means the current is almost zero. We have to, because there is some current here in microampere, but I have approximated that current because the real characteristics is like this. We have seen this, but I have approximated it as a ideal characteristics. I have treated this ID equal to 0, and I have reduced this. I have approximated this 0.7 volt. Okay, so here you can see we will replace this diode as a short circuit, and the voltage across the diode will be VD. Now you can calculate the voltage across the diode. How we can calculate the voltage across the diode? Just by applying the KVL. So if this is plus minus, then this is 5. Let us suppose my current is flowing like this. Even we know that this is open circuited, there will be no current, but for the sake of KVL, I am just stating the current. There is a current. For applying the KVL, I need to take some direction. So this is 5 volt, and this is also plus minus. Then this is VD. Then, and if this is the voltage across this is VR equal to 0, and we know that no current is flowing, then VR will be 0 because no current is flowing. Then this 5 plus VD equal to 0. What will be the voltage across the diode? Minus 5 volt. And if the voltage is across the diode is minus 5 volt, then diode will not conduct and it will be in the blocking state. Okay, so here I am concluding this lecture. In the next lecture, we will discuss the second kind of modeling, which is the constant voltage source model. And the third modeling is the piecewise linear or the constant voltage source plus resistance model. Okay, so here we are concluding this lecture.